Welcome learners to this last session on aldehydes, ketones and carboxylic acids, part 4. This is the fourth and the last session of this series. As you remember, we discussed about the chemistry of aldehydes and ketones in the first two sessions, while in the third session we explained the structure and the nomenclature as well as the preparation of carboxylic acids. In continuation to that, in this session we will discuss today the physical properties of carboxylic acids, the chemical reactions of carboxylic acids and the uses of carboxylic acids. The learning outcomes of this program will be to discuss the physical properties of carboxylic acids and hydrogen bonding present in them and the chemical reactions of carboxylic acids. Now, the reactions can be explained in the four categories. First is involving cleavage of OH bond, where acidity of carboxylic acids will be explained. Then reactions involving cleavage of COH bond, that is CO bond, wherein formation of anhydrides, esterification and conversion to acid chlorides will be discussed, as well as conversion to amides with the use of ammonia will be explained. Then third category of reactions will be reactions involving the carboxyl group, wherein two reactions, that is reduction as well as decarboxylation will be discussed. The substitution reactions will be the last category here, where the reactions at the hydrocarbon part of the, whether it is alkyl group or the aryl group will be discussed, and these will include halogenation reactions or the ring substitution reactions for the aliphatic as well as aromatic compounds respectively. Finally, the learners after viewing this program will be able to describe the uses of carboxylic acids. So, let us first understand the physical properties of carboxylic acids. Aliphatic carboxylic acids up to 9 carbon atoms are colorless liquids with unpleasant odors. The higher acids are wax-like solids and are odorless due to their low volatility. Carboxylic acids have higher boiling points than aldehydes, ketones or alcohols of comparable molecular masses, which is due to the intermolecular hydrogen bonding present in their molecules. This is shown in the structure here. You can see that hydrogen bonds are present in the molecules of carboxylic acids. In vapor phase and in aprotic solvents also, this hydrogen bonding plays an important role and the molecules exist as dimers. Coming to the miscibility, the carboxylic acids up to 4 carbon atoms are completely miscible with water, but the solubility decreases with the increase in the length of the carbon chain, which is due to the increased hydrophobic interaction of the hydrocarbon part with the solvent, that is water. Now, benzoic acid is nearly insoluble in cold water. The carboxylic acids are in general more soluble in less polar organic solvents, that is benzene, ether, alcohol and chloroform and such other solvents. Now, after understanding the physical properties, it is the time to understand the chemical reactions of the carboxylic acids. Very important reactions these carboxylic acids undergo, and we can categorize the reactions into different groups. We will focus on the COOH group, which is the functional group of the carboxylic acid, and focus the reactions one by one. The first reactions belong to the cleavage of OH bond, that is COOH. Now, only focus on the OH bond. The OH bond is being cleaved in these reactions. And the first reaction here is simply the acidity of carboxylic acids, which falls under this category of reactions. So, let us consider the reactions of carboxylic acids with metals and alkalis. Carboxylic acids evolve hydrogen with electropositive metals and form salts, as it has been shown here in this reaction, that carboxylic acids react with sodium metal, which is electropositive in nature, and you get hydrogen in the product as well as a carboxylate ion. And this reaction is similar to alcohols. The second reaction is with alkalis. Here salt and water is obtained, and this reaction is similar to phenols. You can see here that the reaction with sodium hydroxide is shown here, and in the products we are getting carboxylate salt plus water as a product, that is salt and water is a product in this reaction. And with weaker bases such as carbonates and hydrogen carbonates, the carboxylic acids evolve carbon dioxide and form salts. You can see here in this reaction that carbon dioxide is also one of the products, and this reaction is unlike phenols. So, this reaction can be used for their distinction with phenols as a test also. In water, carboxylic acids dissociate to give hydronium ion and the resonance stabilized carboxylate anion. You can see here the resonance structures for the carboxylate ion, where negative charge is equally distributed on the two oxygen atoms. We can write the equilibrium constant K equilibrium for the above reaction as K equilibrium is equal to the concentration of carboxylate ion into the concentration of hydronium ion divided by the concentration of carboxylic acid multiplied by the concentration of water. Or we can also take the concentration of water from the denominator to the side of K equilibrium to give us a new constant, which is Ka, and this constant is called acid dissociation constant and can be now written as K equilibrium into the concentration of water. Rest of the equation on the right hand side remains the same. Since the Ka values are very small, it is very convenient to express them in the form of log values now. So, the strength of an acid is conveniently expressed in terms of pKa values instead of Ka values. Now, what is pKa? pKa is negative log of Ka, and you can see when we compare the pKa values of different acids, we can get an idea about their relative acidity or acidic strengths. For example, the pKa of hydrochloric acid is minus 7.0, whereas pKa of trifluoroacetic acid is 0.23, and it is the strongest carboxylic acid. Benzoic acid has a pKa of 4.19, while acetic acid has a pKa of 4.76. The smaller the pKa value, the stronger is the acid. This you keep in mind for comparing the trends in the acidity of carboxylic acids. Thus, strong acids have a pKa value which is less than 1. Moderately strong acids have pKa value between 1 and 5, while weak acids pKa is between 5 and 15, and those who are very weak acids, they have pKa value greater than 15. Now, we can find a relative order in the acidity by comparing the pKa values, and the general equation or the general trend is like this. Mineral acids which are very strong have pKa values more than the carboxylic acids, which are stronger than alcohols and many simple phenols. And you can see here for phenol pKa is 10, while for ethanol it is 16. You can compare the values and then see which one is more acidic or less acidic. The higher acidity of carboxylic acids than phenols can be explained by two arguments. The first is equivalent structures of the carboxylate ion. We had just seen before also that the charge distribution or delocalization of the negative charge here is on the electronegative oxygen atoms, while for phenoxide ion, which is derived from phenols, the resulting resonance structures are shown here, which are obtained, and you can see that in these resonance structures the charge distribution is not on the same atoms, and also these structures are not equivalent resonance structures. Why? Because In some structures you can see that the negative charge is on oxygen, while in others you can see that it is on the carbon atoms also. And here you can see very specifically that carbon atoms are less electronegative and oxygen is more electronegative, and those resonance structures which have charge on electronegative carbon atom which is lesser than oxygen are less stable and contribute less to the ultimate resonance hybrid. So, that is why there is a difference in the stability of phenoxide ion and the carboxylate ion. Let us next consider the effect of substituents on the acidity of carboxylic acids. Substituents which stabilize the carboxylate ion increase the acidity if negative charge is delocalized by either inductive effect or by resonance effect or by both these effects. Then these increase the acidity of the carboxylate ion. So, electron withdrawing groups stabilize the carboxylate anion and therefore increase the acidity of the carboxylic acid. But what happens if the electron donating groups are present? Destabilize the carboxylate ion and therefore decrease the acidity of the carboxylic acid. So, you can easily compare that if electron withdrawing group is present, acidity will be increased, while if electron donating groups are present, acidity will be decreased. The following groups increase the acidity in the given order, that is trifluorocarbon, if it is present 3 fluorine atoms are present, then they increase the acidity greater than the nitro group, greater than the cyano group, which is little lesser than fluorine, and then fluorine when present increases the acidity more than when chlorine is present or bromine is present or iodo group is present or even a phenyl ring is present. Also, if more number of such groups are present in a molecule, then more will be the acidity. Then we can here see the trend in trichloroacetic acid, which is more acidic than dichloroacetic acid, which is more acidic than monochloroacetic acid. The more nearer these groups to the carboxylic group, the more acidic will be the compound. Here you can see in this both compounds shown here, if the chloro group is present nearer to the carboxylic group, the acidity will be more. The direct attachment of the groups such as phenyl or vinyl increases the acidity because sp2 carbon is more electronegative, and this is contrary to the decrease expected due to the resonance effect shown in these structures here. If an electron withdrawing group is present on the phenyl ring, then the acidity of the aromatic carboxylic acid increases. Contrary to this, the presence of electron donating groups decrease the acidity, and here you can see the pKa values for benzoic acid, and in one case where the electron donating methoxy group is present, the acidity is less and pKa is more, and when an electron withdrawing group such as nitro group is present in 4-nitrobenzoic acid, the acidity is more and pKa value is less and lesser than the benzoic acid for comparison. Now, having discussed the acidity in detail, let us consider the other reactions of carboxylic acids. The second category here is now the reactions involving the cleavage of COH bond. That means CO bond is now breaking in these reactions of the carboxyl group. We will focus on the COOH and we will consider the breakage at the CO bond here. The reactions are very interesting ones. First one is the formation of anhydrides. Carboxylic acids on heating with either mineral acids, that is sulfuric acids or P2O5, give anhydrides. One such example is shown here in this reaction for formation of anhydrides. The second reaction is esterification. Carboxylic acids react with alcohols and phenols in the presence of mineral acids such as concentrated sulfuric acid or hydrochloric acids as catalysts to give an ester. The mechanism of esterification, you can see that first the protonation of the carbonyl oxygen takes place, which activates the carbonyl group towards the electrophilic addition of the alcohol to give a tetrahedral intermediate. Now, focus on the tetrahedral intermediate, and here a proton transfer takes place. Why? This will give you a better nucleophile, which is water here instead of OH minus. So, water will be now leaving from this tetrahedral intermediate to give a protonated ester. The protonated ester on loss of proton yields the ester. Thus, this is a sort of nucleophilic acyl substitution reaction. The third reaction is conversion to acid halides. Carboxylic acids on treatment with PCl5, PCl3 or thionyl chloride, that is SOCl2, get converted to acid halides, and the respective reactions are shown here with PCl3, PCl5 and SOCl2. You can see that in the third reaction the products formed are SO2 and HCl in addition to the acid halide, which was the required or the desired product. Now, here the SO2 and HCl formed are both gaseous. Thus, the reaction with thionyl chloride is preferred because the resulting products SO2 and HCl are gaseous, and therefore, the purification of the carboxylic halide obtained is now very easy. The fourth reaction of this category is conversion to amides. Carboxylic acids react with ammonia to give ammonium salts first, which on heating at high temperature give the corresponding amide, and here you can see that in the reaction the ammonium salts are obtained first, which are ultimately giving us the amides. If now we start with a dicarboxylic acid and the two COOH groups are very close to each other, as in case of phthalic acid, we will be getting finally an imide. After you will be getting first here the ammonium salts, which will be ultimately giving you an imide here. The third category of reactions is now involving the COOH group. Here we will study two reactions. The first one is reduction and the second one is decarboxylation. The reduction reaction is very interesting and you can use a variety of reagents here. Carboxylic acids can be reduced to primary alcohols using either lithium aluminum hydride or better with diborane. Diborane does not reduce the other functional groups such as an ester, nitro group, halo groups when it is present in a molecule. Sodium borohydride does not reduce a carboxyl group. The second reaction in this category is decarboxylation. Carboxylic acids lose carbon dioxide and form hydrocarbons where their sodium salts are heated with soda lime. And what is soda lime? It is sodium hydroxide and calcium oxide in the ratio of 3:1. You can see here the reaction of decarboxylation of carboxylic acids. Alkali metal salts of carboxylic acids undergo decarboxylation on electrolysis also, and this gives us hydrocarbons which have double the number of carbon atoms, and this reaction is known as Kolbe reaction. An example is shown here where you get double the number of carbon atoms in the alkane, which is the product formed. Here you can also see in detail the mechanism of Kolbe reaction, which is an electrolysis reaction, and you can very well see the formation of intermediate free radicals which ultimately combine to give you an alkane of double the number of carbon atoms. Let us next consider the substitution reactions of the hydrocarbon part of the carboxylic acid. Here halogenation is one example. The carboxylic acids having alpha hydrogen are halogenated at the alpha position with chlorine or bromine in the presence of red phosphorus to give alpha halocarboxylic acids. And this reaction is also a name reaction and is known as Hal-Follard Zelinsky reaction. You can see here that alpha halo substituted carboxylic acids are being obtained as the products. Now, if we are using an aromatic carboxylic acid as the starting material, there is interesting reaction in the ring also, where substitution takes place in the aromatic ring. And you can see here that carboxylic group acts as a deactivating and meta-directing group for electrophilic substitution reactions. You can see here two reactions, one is nitration, other is bromination, and we are getting meta-bromo or meta-nitro products when we start with the benzoic acid. But carboxylic acids do not undergo Friedel-Crafts reaction, as the catalyst aluminium chloride gets bonded to the carboxyl group. Having understood the important reactions of carboxylic acids in detail, let us have a glance at their uses. We will explain some uses of important carboxylic acids here. Methanoic acid is used in rubber, textile, dyeing and other important industries such as leather industry and electroplating industry. Ethanoic acid is used as a solvent and as vinegar in food industry. Hexane dioic acid is used in the manufacture of nylon 6,6. Esters of benzoic acid are used in perfumery. Sodium benzoate is used as a very common food preservative. Higher fatty acids are used for the manufacture of soaps and detergents. We hope that this session was quite interesting for you and enriching for you. Now, there are some questions for you to answer. Is benzoic acid soluble in hot water? What is the use of such a solubility behavior? How can carboxylic acids be distinguished from phenols? Give some examples of some substituent groups which increase the acidity of the carboxylic acid and some other groups which decrease the acidity of the carboxylic acid. Is there any method for esterification of carboxylic acid other than Fischer esterification we discussed here? Find out there is one more very interesting method. Why does sodium borohydride not reduce carboxylic acids? And now we will summarize the important key points of this session. Carboxylic acids exhibit hydrogen bonding which affects their physical properties and boiling points as well as the solubility in water. Carboxylic acids are more acidic than alcohols and most of simple phenols. Carboxylic acids can be converted to their anhydrides, esters, carboxylic acid halides and amides. Carboxylic acids also undergo alpha halogenation with chlorine or bromine in the presence of red phosphorus, and this reaction is called Hell-Follard-Zelinsky reaction. Methanoic, ethanoic and benzoic acids are very useful compounds, and we can again summarize how we classified different reactions of carboxylic acids in terms of the breaking of various bonds, that is the cleavage at OH bond or cleavage at CO bond, and then we discussed about the reactions taking place at aromatic ring or in the alkyl side chain, as well as reduction and decarboxylation reaction of the carboxylic acid group. Finally, we discussed the uses of important carboxylic acids. I hope that this session was very interesting and very enriching for you. I thank you for being with us.